Hey guys, 427 here. In this video, we're going to be talking about the heat of formation and how to use the heat of formation to solve thermochemistry problems. We're going to talk about the definition of the heat of formation, and then I'm going to take you through two different ways to solve thermochemistry problems using the heat of formation. The first way, we're going to be using enthalpy diagrams and the equation, and then the second way, we're going to be using energy cycles in Hess's law. Then you can actually use the values to calculate the quantitative value for that. So the definition of the heat of formation is the amount of energy released or absorbed when a compound is formed from its elements. You can use the heat of formation values that are already placed in the data booklet table to predict and calculate how much energy is released or absorbed for a given reaction without actually having to go into the lab and do the reaction yourself. So I've got an example here. We've got elemental carbon and elemental hydrogen reacting together to make methane gas. And if I was going to show this on an enthalpy diagram, I would draw the y-axis, which is enthalpy, and then I could draw a line for the reactants, which would be carbon plus hydrogen, and then I could draw a line for the product, which would be CH4, and then that difference between the enthalpy states would be my enthalpy of formation. So again, all the values are recorded in table 12 in your data booklet. We're going to come back to this as we solve our example for benzene. So the first example, we're going to use the enthalpy of formation data to determine the heat of reaction for the bromination of methane. And we've got the chemical equation written down here. Now I'm going to solve this in two ways. I'm going to use an enthalpy diagram and an equation the first way, and then I'll use the energy cycle, which the IB loves to do it another way. Okay, so if we draw this out, okay, I can put my reactants, and it doesn't really matter where you put these lines. You could put them lower or higher. Okay, I'm going to put my reactants and my products. Okay, and then on the top at the highest energy, I'm going to put my elements, right? Because we're using the elements in the heat of formation reaction. So the heat of formation from the elements to make the reactants, right? CH4 and bromine. Okay, there's a heat of formation there. And then there's also a heat of formation when you react the elements to make bromomethane. There's a heat of formation there. Now, the equation that we can use, if we can subtract these two values from each other, then we can find this difference, which is the enthalpy of reaction. So we're going to use our equation, okay? So the heat of the reaction is equal to the heat of formation of the products, which is this guy right here, minus the delta heat of formation of reactants. Sorry about my sloppy writing. And then that would be right here. If you subtract these two, you're going to get this amount of energy here. Okay? So let's go through it. The heat of formation of products, if we go back to the table and find bromomethane, which is right here, is negative 36. Okay, and then subtract from that the heat of formation of the reactants. So we've got two reactants. We've got methane and bromine. Find methane on here, negative 74.0, and you won't find bromine on here because there is no heat of formation of bromine because bromine is in its elemental state, so it's automatically 0. So minus 74 plus 0. Okay, if we do the math, we find out that the difference is positive 38 kilojoules per mole. Okay, so the heat of reaction is positive 38 kilojoules per mole. That would mean that this reaction is endothermic. Now, I can also solve this problem with using Hess's law on energy cycles, and I'll show it to you now just because the IB loves students to write down energy cycles. So what I'm going to do is I'm going to rewrite my equation. And then up here, I'm going to write the word elements, because we're going to go through the elements to find what the heat of reaction is. So this is delta H. I'm going to call this delta H1. Okay, this is our main reaction. Now, I'm going to find out how much energy it takes to go from reactants back to their elements, and then taking those elements and rearranging them and making the bromomethane. Now, the delta H for this reaction is simply the heat of formation for the reactants to elements, and then this is going to be the heat of formation from elements to bromomethane. Now, we're going to put a negative in here because it's the opposite process, right? We're going from compounds to elements and not from elements to compounds, okay? So I'll call this reaction 2. I'll call this reaction 3. Now, by Hess's law, you know that delta H1 is equal to delta H2 plus delta H3, right? Because 2 and 3 are the subreactions that would get you from reactants to products. So all we have to do is just plug in the values, okay? So delta H2 is equal to negative 74. And then we're going to add that to the delta H of formation for bromomethane, which is negative 36. We do the math, we get positive 38 kilojoules per mole. The same answer that you got from using your equation, okay? So, same problem, just two different ways to solve it. Okay, second example, all right, we've got another thermochemistry question. What is the heat of formation of cyclohexane if the heat of reaction for the hydrogenation of benzene is negative 28 kilojoules per mole, right? So we look at our chemical equation, right? So C6H6, this is benzene. And then C6H12, this would be cyclohexane, just so we know what we're talking about. Now, we're going to solve this in our two different ways. Let's use our delta H of reaction is equal to the heat of formation of products minus the heat of formation of reactants. And then we'll go ahead and solve it with the energy cycle. So I know my heat of reaction, that's minus 208 kilojoules per mole. Okay, I'm trying to figure out what the heat of formation of cyclohexane is. That's my delta HF for cyclohexane. And then my heat of formation for the elements, I need to look up benzene. Let's go back here. We'll find benzene. Benzene is positive 49.0. And then if we add in hydrogen, but hydrogen is 0 automatically because hydrogen is an element. So now we can just do a little bit of math and figure out what the heat of formation is going to be. So I'm going to add 49 to both sides. Hexane. And we do the math. Okay, second way to solve this is using energy cycles. Let's go ahead and write out the reaction again. I'm going to draw elements on top. Okay, and we're going to use our make our cycle, right? So we're going to take our reactants, turn it into the elements, and then we're going to take the elements and turn it into the product, right? So let's call this reaction 1. We'll call this reaction 2. Call this reaction 3. Now, by Hess's law, that delta H1 is equal to delta H2 plus delta H3. Okay, now we know delta H1, it gives it to us in the problem, right? It's negative 208. Delta H2 is just the negative heat of formation, right? Because we're going from compounds to elements, so we'll put that in. That's going to be equal to, let me check again, so it'd be negative 49. And then delta H3, that's what we're actually trying to solve for. We get delta H3, we'll solve it, do the math. Minus 208 plus 49 is equal to the same answer we got using the other method, which would be negative 159 kilojoules per mole. Hey, I hope you liked this video. Go ahead and feel free to check out our website if you need some more personal help, and we will see you later.